Good evening, everyone. We will now be underway with our webcast for this evening, which is on the personalization of musculoskeletal models using medical image data. So to give you a quick outline of the proceedings for this evening, so my name is Anant, and I will be your host. And so I'll start by giving a quick introduction of our speaker, who's Pavel Galibarov, who's a senior consultant here at Anybody Technology. And he will be speaking on the personalization of musculoskeletal models, of course, using these medical images. And towards the end, there will be a few examples he will be showing us which will hopefully give us a better understanding of the concepts that he will be taking us through. This will then be followed with a few final concluding remarks from me, and we will then have the question and answer session. So for those of you who are new to this webinar system, welcome, first of all. And you will see that there's a control panel which should by default appear on the right side of your screen. You can expand and collapse this panel by clicking on the red button, and you can submit any questions that you have via the questions panel, which should also be this box that you see in your control panel. Again, you don't need to wait until the very end of the presentation to ask your questions. You can type them in as and when they arrive, and although we will be taking them up only towards the end. And in case we fail to get to your question in the interest of time, we will surely follow up by email. So for those of you who are also new to the Anybody modeling system, this is a software for running simulations of the human musculoskeletal system. And this is particularly from the point of view of trying to determine the internal loads in the human body during various dynamic movements. And these internal loads are typically things like your muscle forces or your joint reaction forces or forces in certain stabilizing ligaments and so on. And along with the software, you would also see that Anybody is distributed with a managed model repository, which is just a library of these musculoskeletal models corresponding to the different limb segments in the human body. And so each of these models are based on a different cadaver study, but then we've assembled all these models together into one single full human body model, which contains over 1,000 muscles and so on. So the philosophy is to sort of try to capture anatomical details as finely as possible, and this will hopefully give us more realistic results as well from the simulation. There are a wide range of options for you to specify movement in your simulation, and this could be using motion capture data, or in cases where you cannot measure or you lack the experimental hardware to measure the reaction forces. There are also algorithms for predicting these reaction forces. And of course, there is the use of imaging to determine patient-specific anatomy, so to tailor your model to a specific patient. And this, of course, will be the subject of today's talk by Pavel. And finally, you can run these man-machine simulations, which are essentially where you have the human model connected to a model of the environment or some sort of an equipment or a machine that the human is working along with, and then you can run simulations of man and machine as a single system. So we see a wide range of applications for such software, and but most of our customers, we see them in these are classic examples of or typical domains that you would see the Anybody modeling system being applied to. The basic components of the software are these. You can sort of divide it into these three modules. The most fundamental, of course, being the full human body model, or even just a model of a certain limb segment or a part of the body that you are interested in. And then a model of the environment, which is, of course, optional depending on the kind of movement you're trying to simulate. So in this particular example over here, the environment is an exoskeleton. And the third module is, of course, the motion and the forces that you wish to impose on the model, and the condition which form the conditions under which you want to compute the forces. So you combine all three of these into a single full human body model or human environment model, and this is what we call the man-machine model. and you then run an inverse dynamic simulation, which uses certain optimization routines to estimate how muscles are recruited during the movement. And this simulation then gives you the results, which is basically a dynamic sum. Sorry, that video suddenly seems to fail. But this would essentially give you the internal body loads, which are the muscle forces and the joint reaction forces. So in case these loads don't form your final output, you can go ahead and pass this data on to certain post-processing tools such as finite element models. And there are certain interfaces or there are certain tools to actually interface the results from anybody with some of these finite element software. Or in case you are interested in the optimization of your environment, so as to induce a certain desirable effect in the human musculoskeletal system. So for example, if you wanted to design this exoskeleton so as to minimize the muscle activation in a certain group of muscles, then these optimization studies, which would be an iterative optimization study where you keep altering the design until the desired effects are obtained, and these optimization loops can be run within anybody as well. So with that quick introduction of the Anybody modeling system, I will now pass the word on to Pavel, who will tell us more about the personalization of musculoskeletal models. So we will just be giving Pavel a quick minute to come on. And I guess he's here. So I will give the word to him now.
Thank you very much, Anand. Hello, everyone. So let's talk about personalization of musculoskeletal models based on the medical imaging data. So first of all, I will shortly describe what I'm going to talk about today. So the first point on my agenda is to talk about the motivation for subject-specific modeling, why we do that. Secondly, I'm going to cover individualization principles and techniques, and we'll talk about full body individualization and about partial individualization, so we can also individualize body parts. And we will, of course, cover all available tools in the Anybody modeling system. And in that, we are going to provide some examples of how this can be done, and these code examples can be reused by our customers whenever they want to do their own subject-specific modeling tasks. Okay, so let us start by looking at the design of mass and personal products. So mass products target as many potential buyers as possible and frequently do that by offering some sort of customization mechanism. For example, we could think of that, for example, if you look at the car seat adjustment mechanism or adjustable office tables, etc. So design of such product relies on virtually physically using it on a variety of different subjects to take into account human dimensions and various body positions. This is also done by looking at available anthropometric databases, and when we do that, we actually test our product on a single person, but we look at many different subjects. And because of that, we actually design a product that is still somewhat personal but mass-produced. On the other hand, a selling point of a personal product is to provide the best function for an individual. And both mass and personal products can benefit from computational and, in particular, musculoskeletal modeling by virtually testing large number of hypothetical scenarios at virtually no time and cost. Excuse me. So to demonstrate, I picked an example that is actually one of our previous webcasts. My colleague from the Anybody company and from our research group have demonstrated how musculoskeletal models can be used to optimize a car seat and steering wheel adjustment mechanism. This was done for a very innovative car produced here in Denmark, and they did that by analyzing a population of 16,000 individualized seated human models. If you're interested in more details, you can check our YouTube channel and see this particular webcast. But to explain it briefly, basically a large number of different subjects were put into the seat, and the position of the seat was optimized. So the position of the seat, basically after some simulations was found, we found an optimal position of the seat and how it's supposed to be moving for the majority of customers. So most of the described cases can be solved by using linearized individualization schemes. So we can basically scale most of the bones linearly, and maybe this is enough. Well, not completely, because for the same bone length, we could have a very different shape, as you can see on the video. On this video, you can see that roughly the same femur length can have a very different shape. So you can have very small femoral head and a little bit bigger condyles or not. So these differences also affect kinetic configuration of the musculoskeletal system by changing muscle moment arms and potentially muscle activation patterns, joint loads, and so on. And for the products such as medical devices, which require better anatomic congruency, bone shapes play a very important role, and this can also be demonstrated by musculoskeletal simulations. Large medical device companies use bone shape databases to come up with new designs, more robust and more competitive. For example, Stryker utilizes their own SOMA population-based design environment to optimize anatomic congruency for orthopedic and trauma products. Another large company called DJO Surgical use Materialize's ADAM database for population analysis in creating and optimizing the taper-fill hip system, which highlights the need of using more accurate bone morphology information for producing competitive products. These designs can also be tested using multi-scale computational schemes. For example, anybody modeling system can be used as one of the components for multi-scale modeling. Multi-scale modeling requires consistent geometries in musculoskeletal and finite element models to ensure correct muscular and joint reaction load onto the FEA model. And such consistency is very important, especially for the load-sensitive tasks such as bone remodeling, for example. So on this slide on the left, you can see a musculoskeletal simulation where we have our human walking, and on the right you can see the finite element model. So our loads were transferred to the finite element model. Anybody Technology, together with our partners from Materialize and ANSYS, have developed a set of tools and workflows that can be used to set up a multi-scale model. If you are interested in one of the multi-scale workflows, please contact us or watch a recorded webinar for more information. Another reason to use subject-specific models is to enable applications where anatomical accuracy is a must. For example, preoperative planning system requires anatomic accuracy. We participated in a European protocol TLM-SAFE where this consortium created a prototype of a preoperative planning system which also used any-body modeling system as a part of it. And what you can see on the screen is that personalized musculoskeletal models were superimposed with the MRI images to show the quality of these models. And this information can also be used for further preoperative planning and even for intraoperative manipulations. So it is clear that geometrically accurate model somehow improved the accuracy, but what is the result of using subject-specific models? And one of the good examples that we refer often is the winner of the 5th Grand Challenge competition to predict knee laws. In this particular work, authors used a subject-specific model that was based on the medical images, on the available medical images, and together with some other improvements that guaranteed the best results in this particular competition. Our next webcast will be presented by the winner of the following year's Grand Challenge competition, where they also used an individualized musculoskeletal model to model the knee contact. Knee contact modeling and modeling contact in general is a complex technique and often requires precise surface information. And this is also not possible without subject-specific scaling. I just want to make a small disclaimer that the personalization scheme that was used in the upcoming webcast might differ a little bit from what I'm presenting right now. So there are certainly many ways to do that, and they chose slightly different ones. So I look forward to see this webcast as well. And on this note, I will stop with the motivation. I hope I convinced you that model personalization has a lot of potential and opens many new doors for improving product design. So let's try to look now at the way how we can personalize a model in the anybody modeling system. So the personalization scheme. When we are given a task of simulating human, first thing that we do is we change the height and the weight of this model to roughly match our subject. And this is always the initial step, and it can be done in many different ways. For example, you can basically specify only the height and weight of the subject, or you can have individual body parts measurements and insert them into your musculoskeletal model. Or you can also use motion capture data and optimize the lengths of the segments. Secondly, when we are happy with the overall size of the model, we want to look into more details, and depending on available data and the task we are facing, we may want to personalize different body parts, and I will call them segments from now on. Personalization is also a must when we have to solve contact problems, as I said. This is when we will use all available surface information for the contact. And finally, we could actually use much more information, and for example, we can use muscle volumes to correct default scaled muscle strength. We can change muscle attachments based on the MRI scans and possibly ligament information, but generally speaking, this data is not always available, and because of that, I'm going to focus mostly on the first two steps, on the anthropometric scaling and on the individual bone and all the soft tissues that are attached to this particular bone morphine. And this scheme just once again highlights the workflow. So we start from the full body scale, go to the bone level, and then we go and change the muscle attachments and other small details. So I think I spent a few minutes explaining what needs to be done for the personalization, and it probably sounds very complex. And if you look at the model, and the model looks very detailed as well, so we have a lot of muscle attachments, we have a lot of muscles and a lot of segments, and that probably requires some work to do. And does it take, and I'm wondering, does it take a lot of time and effort to model for a new person? And we think that the answer is actually no, because we organize the model in this particular way that it allows for quick individualization. For example, we implemented basic anthropometric scaling laws that would only require a few numbers, a couple of numbers. For example, the height of the person, the weight of the person, and the fat percentage. Or it can use, of course, a few more numbers if you have available lengths of the segments. But if you look at the body part individualization or segment individualization, it is a little bit more complex, but in reality, we never start from scratch. We always reuse our code. And because of that, the task becomes just to look in the tutorial, copy a piece of code, and just repeat it. And today I'm going to talk, in the end of this webcast, I'm going to present a couple of different solutions that are quite common, and they basically complete, together with the tutorials, they complete a set of most probable scenarios that you could face. And I'm going to show how the models are constructed, explain what is done, and later on we will share all those models. Okay, so let's look at the model architecture. So an anybody model is organized as a tree. So different branches of the tree contain different objects, and for example, one of the branches contain an anthropometric scaling law. What you see on the right is a pseudocode, so it's not an actual code or anything, but just to show you that we have a folder that contains anthropometric law, scaling law, then we have a certain body part, and then we have inside of it we have something called scaling function. And this scaling function is a function that is applied to a position vector and basically changes this position vector to be something else. And this position vector is actually a position of let's say, one of the muscle attachment nodes that is actually inside of the segment, which corresponds to a certain body part that you see at the bottom. Right. So what you see at the bottom is that the scaling function that I found in the anthropometric scaling law, I used to apply it to a muscle attachment location, which is quite standard. That means that we simply deform the model. And you don't actually need to worry about any of that because it is all organized and connected automatically, so everything is being picked up automatically. So this is all done inside of the model, so you don't even see that. All of that starts with the anthropometric scaling. And we have several different schemes for anthropometric scaling. We have a standard scheme, which means no scaling at all. So this is our standard anybody model, or we also call it generic anybody model. Then we have a uniform scaling law, and we have scaling laws that are based on the length and mass and fat percentage and some external measurements. And you can get different subject sizes. So internally we have a piece of code that defines this structure. And maybe again this looks a little bit scary, but I just want to explain you the principle. Please do not concentrate on the text itself. But what I want to show you is that inside of the scaling law we have folders that are related to the mass scaling, to the strength scaling, to the fiber length scaling, geometrical scaling. And in case of the standard, all of the scaling factors are equal to 1, and because of that, no scaling is happening. And in order to turn on this scaling law, we can specify a line like that, which is also described in the tutorial, where we simply say that our scaling law should be standard scaling. This is also a default option, so we don't even have to specify this one. And if you look at the uniform scaling, it becomes a two-line definition where we specify that we want to use a uniform scaling, and then that we also use something that we call an anyman file where we have anthropometric measurements, for example, the body mass and the body height. And in case we have the actual segment length, so we can also specify the length of a particular segment. And again, this is something that is done internally in the model, so you wouldn't even see that. And there is more information in the tutorials, so you can learn about all of that. So let's assume that, we can now do a uniform scaling. And I think it's quite simple. So what you need to do is to define a couple of lines and copy a file from an existing model where you specify the body mass and body height. And that is effectively enough to define our anthropometric scaling law. So we can continue, and we can now switch to the individualization of the segments. Let me remind you why we do that. So first of all is to gain more accuracy, and secondly we can take into account individual bone morphology, and we can change the muscle moment arms and so on by applying this personalization scheme. And we can also make a musculoskeletal bone surface consistent with a finite element model that, and we can use that for further load transfer when we decide to go into multi-scale modeling mode. We can also employ bone and cartilage surfaces reconstructed from CT, MRI scans for contact analysis. So, and because of that, this is quite important, and we do it quite often. So how do we do that? If you remember from a few slides back, I said that our model is organized that we have an anthropometric scaling law folder somewhere which contains a scaling function, which is a 3D function that is being used to process our muscle attachment nodes. And as you can imagine, because we are going to individualize our segment, we are actually not going to use the same function again. So what we need to define, we need to replace this particular function with another one, another 3D function, which we call a custom segmental scaling function. So let's try to think how do we individualize something. So we define a function that will make an any-body generic bone look like the target bone that we have in mind. And it also should ensure that all entities on the surface and outside deform in such a way that they match the subject's anatomy, that all the muscle attachments are in the right place, and that bones look the same, and that overall muscle volume is the same, and so on. And if you just think about that, we are talking about several volumes that should go from one state into another one. And the solution for this kind of problem is a 3D inter or extrapolation function. It can have a linear or non-linear behavior, and we should have some sort of control over the interpolative and extrapolative behavior. This is what we use for subject-specific scaling. We have several classes implemented in any-body modeling system, where we have a set of linear scaling functions, and we have non-linear functions that are based on the radial basis functions. And it is also possible to use combinations of all of these, and we can assemble them into a pipeline. And I will describe one of the most useful pipelines that I use all the time in a few moments. But let's talk about the linear functions. And the linear functions is just a normal linear function that takes a vector x, which has 3 components, and transforms into another vector which contains 3 components. And this is all wrapped into 3 different classes. These are the basic classes. We have more, but these are the most useful classes for morphing. So one of them explicitly defines a scaling, a 3D linear transformation. So we have a scaling matrix A, and we have an offset B here. And if we keep the default values, that would be equal to another class that we have, and which is called 3D identity transformation. And we have a second variation of the linear transformation where we provide 2 sets of landmarks, and these are corresponding set of landmarks, and each point in each set correspond to the same point in the other set. And what we can do, we can solve a least squares problem where we'll position the source points into the target points in a certain manner. And for example, because we use an implementation from VTK library, we can do it in the rigid body mode, we can do it in the similarity mode, or also called uniform mode, and affine mode. And that basically computes this A and B automatically. These are very useful classes. I will explain in a second how they can be used. But let's have a look at the nonlinear functions. Basically, it's a nonlinear function that defines interpolation, and we chose to use RBF functions. So the interpolation transformation is given by this formula. So we have like a kernel matrix, a kernel function where we have distances between 2 points, and it is being multiplied by a coefficient which is unknown, and we also have a linear term that also is used in this interpolation. So basically we can have interpolation transformation that is defined like that, but we don't really know the coefficients. So what we can do, we can actually use our source and target landmarks to find these coefficients. And this is how the function actually works. So we provide 2 sets of source and target landmarks to define our transformation. And once we provided those and selected some parameters, our interpolation transformation is ready to use. We have 2 variations of this transformation. One is called anyFun transform 3D RBF. It's just a function. It's a RBF function where we provide 2 sets of landmarks, as I said. So we provide the source landmarks and we provide target landmarks. And here we specify the degree of the polynomial in this transformation that I mentioned. All other parameters look very scary, but mostly there are some different parameters that you can set, but you don't have to use all of them. We also have a variation of an RBF function that uses 2 STL surfaces, and it uses these STL surfaces to find corresponding set of landmarks automatically, but it requires these surfaces to be pre-registered to each other using a pipeline of transformations. And again, you only need to provide the source and the target surface and polynomial degree. So as I said, we could use a pipeline of transformations, and this is a very important concept in subject-specific scaling, because we could use different levels of subject-specific scaling. So we can start by scaling bonds anthropometrically, and then we will use a single linear transformation. And then we can also do another level of scaling by, let's say, employing some linear uniform scaling functions just to improve the size a little bit more. And then we could do a rough nonlinear transformation where we use only a few points, a few landmarks for the RBF transformation, and that will deform our surface a little bit more. And then we can also employ surface-based nonlinear functions. We could also move objects forth and back from the segmental to anatomical reference frame to CT MRI reference frame. Probably doesn't make sense right now, so I'll try to visualize what I'm trying to say. So for example, just imagine we have an antibody source bone, and we selected several landmarks on it. And we have a target bone, and we want our source bone to deform into the target bone. So by using a linear scaling or registration transformation, we can basically construct any fun transform 3D linear, and by subjecting our surface to this transformation, we will get a picture like that. So our 2 bones will align. It already looks quite good because linear transformation worked quite well, but what you can see is that the greater trochanter has a rather large error. I think that can be up to 3, 4, 5 centimeters. And that's a rather large error for the moment arms, muscle moment arms, because there are several muscles that are connecting to the greater trochanter area. And because of that, we want to do a further improvement. And basically, we could use the same landmarks and construct an RBF transformation. And what you can see here, that we actually get a slightly better match, but the error is still probably up to 1 centimeter. And I think probably from this perspective, you can't see the largest error, but it is also present. So what we could do, we could actually use our STL to STL RBF transformation to get even better match. And on the right hand side, you can see our generic bone being transformed into the subject-specific bone, and you can see the difference of volumes. And you can see that the error is rather small. And since this is an interpolation, extrapolation transformation, all our muscle attachment areas and via points and all other working entities move along with the bone. So I was talking a lot about the pipeline of transformations, and this is how it looks like. It's a little bit simplified, and but it still looks quite scary. What I want to say is that you actually don't need to worry about that, because this is the piece of code that remains constant all the time for almost all bones. So what you would need to do is just to copy this block of code somewhere and then just adjust it to your needs a little bit. And just to connect the dots with the images that we had on the previous slide, we can show that constructing a linear transformation using two set of landmarks leads to this picture. And we have a non-linear transformation using landmarks as well, and that gives the second picture, and the STL transformation corresponds to this picture. And just to reiterate again, this code can be reused and it regularly changes. And only input to this code is the two sets of landmarks and file names. So the next step, now we created a 3D scaling function that will basically process all muscle attachments in the new way. What we need to do is we need to use this function and add it to our human model, because at the moment we actually have an anthropometric scaling that will be used as a scaling function. So we need to replace it, and this can be done using this approach. So we basically specify to the system that we actually want to use a custom scaling for one of the segments, and then we basically say we access the same folder. As you can see on the left, I have a model tree where we have scaling and we have geometric scaling, and it was supposed to be a pelvis segment, but for some reasons I have selected trunk and the scale function. But we basically access the same folder and replace the scale function by something that we want. And that is all, and this technique is applied for every bone that we want to individualize. And this is also described in tutorials, and it actually has more information. So if you're interested in trying, so please have a look at our tutorials. So let's summarize how we individualize our models. We choose an anthropometric scaling law. We specify what kind of scaling law we want to use. We specify the basic measurements of the human in any man file. And if we want to do individualization of the segments, so we construct a 3D transformation pipeline, as I described before. And typically we only provide two sets of matrices that contain landmark coordinates, both source and target, and we provide two file names for the source and target STLs. And after that we simply connect the dots with our model by incorporating the scaling function into the human body model. I want to mention that it is possible to automate this individualization process, and what it means is that we normally need to specify landmarks to define our interpolation functions. And we can actually select these landmarks automatically if we have the right input. For example, if we have our source bone and our target bone in the same topology, and when I say the same topology, I mean that we have the same number of vertices and faces, and the vertices have consistent locations, so they repeat all the landmarks. Then we can simply select landmarks from such STL surface, and after that it comes down to basically specifying the name of the STL file, or it can be wrapped into a subject ID. And that also highlights that we can potentially use ADAM datasets, information from SOMA environment, and we internally use PCA datasets. And the example on the right is actually a PCA reconstructed dataset. So we actually morph a model to 21 different subjects by specifying a subject ID only. And in this particular example, we actually look at femur population from -2 to standard to average to +2 standard deviations. Okay, so it is now time for the demo. So we have a hypothetical scenario where we have an available CT or MRI scan, and we could reconstruct a femur surface. We could segment it out of the CT or MRI scan, but we only could segment out proximal surface of the tibia, and nothing else was available. And let's assume we have a walk-in motion capture data file. So our task is to build a subject-specific musculoskeletal model. We are going to skip the anthropometric scaling because it is explained in the tutorials, and I said it's just specifying a few numbers, so it's rather simple. But what we are going to look at is how to morph our femur, our generic femur, to match the subject's one. And secondly, we are going to morph our tibia in the best possible way based on the information that we have on the partial surface of the tibia, on the proximal part. And as the last step, we will combine motion capture data with we'll combine the optimization of the segment length from the motion capture data, and we'll combine it with the femur morphing. And I will show it in a second. So let me switch to the Anybody modeling system. So this is a basic Anybody. This is one of the simplest models, standing models. So it has nothing, just a human standing, as you can see here. And I made a small add-on for this particular example, and I called it demo. And I simply added scaling, and as you can see, it's nothing special. It's only a couple of lines of code. And if you look inside, you may still recall the inclusion of a custom scaling function into the human model. And this is the code that we do. We specify to the system that we want to use custom scaling for the right femur. And after that, we basically say that we make a reference to the interpolation function that we create inside of this file. And if we open up, we see something familiar. We see a pipeline of transformations. And as I said, this pipeline is quite standard, so nothing changes. But in this particular case, I made something interesting. So I made an automated selection of the landmarks from the source and target STLs. And I did that just to demonstrate how everything can be done automatically. Because a normal procedure is described in the tutorials and was less interesting, so I wanted to cover more cases. And because we are going to provide these files at the end of, maybe not at the end of the webcast, but we will prepare a good package and we will put it on our wiki page. So what you can see here is that the first block that I will select is basically just a selection of landmarks. So we extract some vertices from the STLs, And secondly, we just feed it into the pipeline of transformations, and then we include this new scaling functions into the human model, and after that we basically can see the result. And you can see it here. So what you can see is you can see a short femur. So we morphed the right femur, so our right femur became a little bit shorter. And you can see it because we also have the original left femur still in the model. So you can see that it reduced by 5 centimeters or so in length. Just to demonstrate, I actually had two subjects. I had a female subject which has a short femur, and I have a male subject which has a longer femur. So let's have a look what happens if I change the STL file. So I expect to see my femur to become a little bit longer and change the shape, and this is what happens. And as I said, this is the automated morphing that can be implemented in anybody. So the code doesn't change, you only change the file name. As a second part of my demonstration, I wanted to morph tibia based on the proximal surface. And if you look inside of this file, we again see that we include some scaling function into our human model. And if you look inside, we have a little bit more happening on these few lines of code. If you look at the bottom, we can still see that we actually have a pipeline of transformations, and we feed two sets of landmarks to this pipeline. But this time we actually construct our landmarks a little bit different. So we split the source landmarks into two sets. We split the landmarks into proximal and distal groups. And because we have a corresponding set of proximal landmarks for the target bone, so what we are going to do is actually we are going to scale the bone anthropometrically. We are going to scale all the source points anthropometrically, and then we are going to register our new surface to the proximal part, and we are going to adjust all the landmarks based on this surface information. And this is just an example of how it can be done, so you can actually read this code a little bit more. I think I will put a little bit more documentation what is happening exactly, but effectively the task is just to create two sets of corresponding landmarks, and then we feed it into the pipeline of transformations. And it ends up in a picture like that. Just give me a second. So if I reload it, what you should see is that our tibia changes a little bit. Yes, as you can see, it shrank a little bit and now has a almost similar size to the green surface. And this green surface is actually our proximal tibia that was reconstructed from the CT scan, from the partial CT scan. As you can see, the morphing is not perfect, but I haven't spent too much time on selecting landmarks properly, and probably I didn't have many of them. It was only done for the demonstration purpose, but it still shows that the size is now scaled much better, and we can actually use the green surface to define our context, so we can actually neglect the morphing and use our green surface to define the contact of the knee joint. And I think that concludes my second example, that you can do a partial scaling of the bone. And I guess this is the best we can do with the information that we have. We don't really know anything else. So I think that's quite good. So our last example is actually a motion capture data, a motion capture model, where we do something interesting. So we say that we know the shape of the bone because we did it in the previous example, in the standard model example. We know how to scale femur, but we actually don't know the length of the femur, the overall size. So we say that we want our femur to look like the one in the standing model, but we want it to be a little bit different. So we want it to be optimized based on the motion capture data. So the actual size of the bone will be optimized. And this is done in exactly the same way as I explained. So we include our scaling law into the human model, and we have our pipeline somewhere here, if you remember. And but what we do is actually connect the scaling law at the length of the bone to the optimization parameter. So we have an optimized length parameter that has been picked up by the optimization of the system of this model, and yeah, and we define a scaling factor. So let's try to load it and see what happens. If we load it, we cannot actually see much because the bone is deformed and it has a slightly different shape, but it's really hard to see. But what we have is actually the scaling factor, and this scaling factor shows the difference between our scaled bone and the initial guess of the optimization. So I will find this factor, just a second. So as you can see, it's 111%. So our femur was quite short, so to match it with the initial guess on the femur length, we needed to multiply it by a factor of 1.11. So what I'm going to do, I'm going to start my optimization, and we should see that this number is changing, that this scaling factor is being optimized. So I think it will take a couple of loops of the optimization before the numbers change, but just to convince you, I will do that. So we can see that the bone is changing. And I think by the end of the optimization, we should get 109%. So we started quite close, but it wasn't exactly the perfect match. Just, I think just one more second. I think the next optimization loop will actually change this number. I will just show that this number is being optimized and that we actually get a slightly different shape. Anytime now. Okay, as you see, the number has changed from 111% to 110. So after a few loops, we'll actually get our number. So I will stop it here and go back to the presentation. And this is here basically just a quick explanation of what we did. So for the first step, we automatically selected landmarks, and this is the interesting part. Then we fed into the pipeline of transformations, and for two different subjects we saw a difference. So we had a short femur and a long femur, and the only thing that we did, we changed the name of the STL file to do so. And in the second part, we also just constructed two sets of landmarks that we fed back into the pipeline of transformations, and that gave us an individualized model again. And as the last part, we created a slightly different scaling function that also used some optimization factors in it. So just to conclude everything, one can use bone surfaces segmented from CT, MRI to personalize and improve musculoskeletal models. And the procedure comes down to several steps. First of all, we always reuse our code, and normally all the code is available already, so you don't actually have to implement much. And secondly, what we do is we just select a corresponding set of landmarks in an automated or semi-automated manner. And in special cases like the motion capture model, we could combine different geometric information to fill the missing gaps. All in all, I think that personalization gives a great value to the musculoskeletal modeling tasks, and it comes at a relatively low cost. And now we have time for questions, so I would also like to acknowledge my colleagues from University of Ghent and University of Regensburg for providing the data, and some TLM Safe project colleagues who helped in developing some of the models here. So please visit our YouTube channel and our website for more information. And I will pass word back to Anand.
Thank you for the great presentation, Pavel. And I will just take a minute here to shift everything back to my screen, which should be right about now. Yep, I think it's up. So just a few closing remarks before we move on to the actual question and answer session. Firstly, if you do have any questions, this is a great time to formulate your thoughts and type it into the question box, and we will be picking them up shortly. So the next webcast will be scheduled is scheduled for the 3rd of May. And this is on the prediction of knee joint contact forces using force reaction elements. And these were the winners of the 6th Grand Knee Challenge, as Pavel had mentioned in his presentation. You can check our YouTube channel for other webcasts that have been previously broadcast. And of course, just search in the channel search field, just search for Anybody Technology. You can visit our website for future events and an updated list of publications. And you can visit www.anyscript.org, which is which contains a wiki page and also a forum, a user support forum. And this wiki page is also the one that Pavel mentioned earlier in this presentation, where we will be uploading the model very soon. Some upcoming events are we have a workshop at ESB, the European Society of Biomechanics, which is in Lyon this year. And coincidentally, it's Pavel and myself who will be hosting that workshop as well. And this is on the this workshop is those who are into finite element modeling and multi-scale modeling in general would find this interesting, because this workshop is on how you can use the information from musculoskeletal models to actually create better multi-scale models of the human, of different organ systems or organs in the human body. And in case you cannot make it to the workshop, but if you will still be coming to the ESB conference, please stop by our booth and say hi. Apart from this, there is, if you are going to be in Sweden for the ICRA 2016 conference, again, please stop by and meet our representatives. And there is also a musculoskeletal modeling course, which will be held at Aalborg University. And this will be managed by our sister group, which is the Anybody Research Group, which is centered at the university over here. We are the same town, but we work here at the company, which is Anybody Technology. And you can go over to the university's website, which I must apologize that I should have probably added the URL over here. But details of this course can be found if you navigate to the Aalborg University page and search for the Anybody Research Group. So on that note, we will now, I'll now just bring Pavel in as well, and we can then get started with our question and answer session. Pavel, are you here?
Yes, yes, I'm here. I see a couple of questions. I'm reading the first one. So I have a question. Can we pick landmarks in Anybody software, or we need to use external software? Yes, you can pick up landmarks in Anybody, but it may not be the easiest way to do. So I normally pick it up in some external packages, and there are fantastic packages like Mimics and MeshLab and many others. So you can actually do that, and I think next generations of Anybody will simply read those files in, and I think it's another question is, could we clarify how we can unify the number of vertices for the target and source segments? So one way to do this is actually to do an RBF scaling of the target bone back into the source bone, and this way we will get our topology, the right topology. So.
Great, thank you. I have a few questions over here as well. So someone here is interested in knowing what are the best set of external landmarks for. So you mentioned about selecting a set of points on your model, on the bone in your model, and then a set of corresponding points on your medical image. So is there an optimal set of landmarks that you would recommend for each individual bone? Does such information exist somewhere?
We actually worked on something called landmark protocols for some time. But the difficulty with this one is that if we have some sort of pathology in the, let's say, in one of the bones, then the protocol doesn't work. And because of that, we haven't spent much time on finishing those protocols, but we are still working on them. And I think for the healthy bones, it's a really good idea. I think the protocols are somewhat available for the low extremity bones and pelvis. So if you ask us, we could basically share the information on those protocols. Yeah,
Great.
I think, yeah.
Thank you. So another question that we have is, so you mentioned on how patient-specific scaling could actually help you generate better congruent bone surfaces at certain joints, such as the knee joint, for example. And you also mentioned that this could be used for contact-based analysis. Now, can any such contact-based analysis be done in any body?
Yes, of course.
Okay, could you elaborate a little more on that? On what kind of, on how you could use this information inside any body?
Basically, we have a set of. I think I'm not going to spend much time on that because we are running out of time.
Sure.
But we have a set of webcasts where we actually talk about contact modeling in general. So please have a look, and I think it's well described in those webcasts. So I think it will be much more informative.
Great. So probably let's just take the last couple of questions now. The next question is on have you tried scaling very thin bones? And so this particular user is interested in the scapula. And are there, because the scapula being a very thin bone, are there any specific consequences that we may have to look into?
Yes, we have, of course, tried to scale very thin bones, and we work on the pelvis. And if you remember, I talked about the pipeline of transformations, and the second last being STL to STL morphine transformation. And in this particular case, it doesn't work very well because the closest point algorithm that is implemented inside flips the points forth and back. And because of that, we actually stop at using just the landmarks, and that gives us reasonably good match. You may need to use a few more landmarks, and I think that might solve the problem. But this can be done as well, I believe. Yes.
All right. Thank you. So on a final note, I'm going to be a little selfish here and try to squeeze in something from me. And something I was thinking of, and this is probably more of a comment than a question, but I would like to know your thoughts anyway, is on when we're thinking of subject specificity. I think it is also important for users to think of how far or how detailed they want their models to be. As to whether you're trying to spend a lot of time, I mean both computational time as well as your own personal time, in trying to customize your models to an extent which is not, which probably does not yield a justifiable improvement in the accuracy of your simulations. So are there any general design principles or a rule of thumb or something that we need to keep in mind while doing this? And
yeah, that's an excellent question. I think I think it's quite difficult. Well, one way, of course, like if we look at the finite element models and how they, for example, estimate the mesh density, so they have some sort of convergency analysis where they keep going until they converge to a certain value. And I think in our case, it's a little bit more difficult to do something like that. And because of that, normally we stop at a certain level where when we think that like the model is good enough. And for example, I wouldn't stop at the linear scaling as I showed on one of the actually on the image that you see on the screen. For the left side, the error is still quite large, so it's actually a few centimeters, which introduces a rather large error in the moment term. So, and because of that, I would still go with the nonlinear scaling. Normally, you can just assess it visually. So, for example, the right hand side looks actually pretty accurate, and the errors that we see, and you can judge them by the intersection of volumes, it is actually quite low, so the surface is almost identical. But generally speaking, it is actually not difficult to go all the way to the STL surface if you have the data. So if you have the data, I would recommend to use all of it, because I think it comes almost for free.
Okay. Great. So unfortunately, we need to truncate this question and answer session with that one. And for those of you whose questions have been unanswered, we'll surely follow up by email. And I'm sorry that we couldn't address them right now. And thank you, everyone, for attending. And we hope you will join us very soon for our next webcast on the 3rd of May. Good night.